Welcome to this second video on networks with power law degree distributions. We will talk about some of the mathematics that governs the properties of these power law networks. In our previous video, we described power law distributions and noted their apparent prevalence in large complex networks. And here is an example of a network whose degree distribution seems to be governed by a power law. The network itself consists of many low-degree vertices connected by a small but measurable collection of hub vertices with a very high degree. The log-log plot on the right shows that the degrees of this network would correspond to a power law for exponent alpha is equal to 1.5. And this value is actually below the typical range of so-called natural power laws. Exponent values between 2 and 3 are more typical for real-world networks, and today we will give some mathematical evidence for why this is the case. In our previous video, we spent some time comparing the structure of a network whose vertex degrees have a bell-shaped distribution with the structure of a network whose degree distribution follows a power law. Such a power law distribution is an example of a distribution that has a fat tail. The decay rate is slow enough so that there is a measurable area under the tail of the distribution. In our network, this fat tail corresponds to the sprinkling of hub nodes with massive degree. Here's the probability mass function that governs a power law degree sequence. The probability p sub k that a vertex chosen uniformly at random has degree k is proportional to k to the negative alpha. Taking the log of both sides shows that log of p of k is linearly related to log of k. The slope of this line is negative alpha, and this is why we get a line with negative slope when we plot a power law using a log-log scale. When we look at real-world data with a nice fit to a power law distribution, we find that there is a pattern in the exponents. Most naturally occurring power laws have an exponent that lies between 2 and 3. So let's dig into the moments of a power law distribution to see what is so special about this range. For simplicity, we are going to approximate the discrete probability mass function with a continuous probability distribution function. In other words, we'll allow our random variable to take on non-integer values. As you can see from the plots of the PMF and the PDF, the corresponding areas under the functions are basically the same. Our calculations are going to go much more quickly when we can use integration instead of summations. So let's give ourselves a break and use the PDF to get a general idea of what's happening. You'll recall from our discussion of probability that the moments of a distribution tell us about the shape of that distribution. In particular, the first and second moments of a distribution tell us about the average value and about the spread of that distribution. Here is the general formula for the mth moment of a continuous distribution that takes on values between 0 and n. To get the mth moment, we integrate x to the m along the probability density function p. In our case, the continuous power law PDF is some constant times x to the negative alpha. Evaluating this integral is a fairly elementary computation, and here we assume that minus alpha plus m is not equal to negative 1. The result is some constant d divided by n to the alpha minus m minus 1. And for us, this maximum value n corresponds to the size of our network. So let's calculate the first and second moments of our distribution. The first moment is just the expected value, or average value, of the distribution. We see that the expected value is d over n to the alpha minus 2. Now let's run a thought experiment for a power law network whose exponent is greater than 2. According to this formula, what happens to the average degree as we increase the size of the network? Well, since alpha is greater than 2, the expected value is d over n to some positive power. So the average degree tends towards 0 as the network size increases. This means that the vast majority of the vertices in a natural power law network have very low degree. If this weren't the case, then the average degree couldn't possibly be near 0. And this matches one of the defining features of our real-world networks. Most of the vertices indeed have very low degree. Now let's talk about the second moment. The second moment of a distribution is comparable to its variance. In other words, the second moment tells us whether the distribution is mostly concentrated around its average value or if it takes a wide spread of values that can be very far away from the typical value. And we are interested in the natural power law sweet spot, so we want to know about the second moment when alpha is strictly less than 3. We can see that the second moment is d over n to some negative number, which is the same as d times n to some small positive number. Now let's allow the size of the network to grow as we did with the first moment. This time we get the opposite effect. As the network grows, the second moment grows as well, and this means that the spread of degrees increases without bound. In other words, even though most vertices have very small degree, there are a smattering of vertices of incredibly high degree. In other words, we have a bunch of hub nodes. Furthermore, the hub node degrees are so high that they dominate the network structure as they quickly fuse the network together into a tightly connected system. These two observations about the first and second moment explain why the natural power law sweet spot between 2 and 3 makes sense for real-world networks. Alpha being greater than 2 ensures that most vertices have very low degree, and alpha being less than 3 ensures the existence of those very important hub vertices. And this ends our tale about natural power law exponents. In conclusion, we have used the moments of a power law distribution to show that the natural power law exponent range between 2 and 3 is precisely what we need to ensure that most vertices have small degree and that our sprinkling of hubs is dense enough to fuse the network together. Our next video is about the self-similar and fractal-like qualities of power law networks. And as we finish this video, this is a great place to remind you that power law networks are an idealized model and that reality is much more complicated. The simple principles that describe and govern an idealized power law will give us a baseline understanding that we can use to guide our inquiry into complex networks in the real world.